So in the next 45 minutes or so, I'll try to give some highlights about the way mathematics developed in India, what are its special features, and what's the contemporary relevance of this Indian mathematical tradition. The title is chosen intentionally. Normally people will say development of mathematics in India. I have called my talk as development of Indian mathematics because there is something that we can call as Indian mathematics, and this perhaps some point which will come through a little bit. Mahaviracharya was a great scholar who flourished in the Rashtrakuta Empire, in the Amoghavarsa Nrupatunga's kingdom. He was a Jain scholar. He wrote the work called Ganita Sara Sangraha in 850 AD. And he is trying to explain what is the centrality of mathematics, Ganita. So basically he is trying to say that in all aspects of life, in all technical disciplines, mathematics is indispensable. It's sort of yatkinchid vastu tat sarvam ganitena vina nahi. Whatever is there in the three worlds, there is nothing that's without mathematics. Be it in astronomy, be it in warfare, be it in commerce, be it in architecture. Like that he goes around. This is one of those usual standard ways of explaining the centrality of Ganita. Indian mathematics is called Ganita. And what is Ganana? So one of the famous commentators, Ganesha Devagnya, who hails from Nandigrama in Maharashtra, he defined Ganita as Ganyate, Sankhyayate, Tat Ganitam. So mathematics in India is the science of calculation, or to use a more contemporary word, science of computation. And the main thing that mathematics texts in India do is to give beautiful, systematic, efficient, interesting, commonly adoptable procedures for doing calculations. So this is a very ancient rule for squaring, which I am quoting from an ancient astronomer and mathematician called Bhaskara, who is different from the Bhaskaracharya of 12th century. This Bhaskara is a commentator of Aryabhata. This is a very ancient rule where he is saying in order to square a number, you square the end digit first, multiply the end digit by twice the other two digits, write them above them, then shift the entire thing by one place, cross out the last digit, square the next digit, multiply twice the last digit with the other digits. So a systematic procedure like that, which will give you the square. The crucial thing you can see is, this is one of the very ancient rules for squaring. If you square an n digit number, in the normal ways of squaring, you do multiplication of n digits with n digits. That is, you will do n squared multiplications. But even the most ancient rule for squaring that is given in Indian text, he is saying you have to do only n into n plus 1 by 2. So already you have reduced the order of magnitude of computation by a factor. And the essential use that is made here is the fact that you have a place value system. We will come to it in a minute. This word algorithm that we very commonly use today has a very strange history. Algorithmic methods which came about in Europe in medieval period, they overshadowed what was called the Abaxist method of calculation. And the word algorithm goes back to the works of one Central Asian astronomer, mathematician called Al-Khwarizmi. He wrote a book in 850 AD which got transmitted to Europe, and the method of Al-Khwarizmi became algorithm and became algorithm. And what was the book of Al-Khwarizmi? Al-Khwarizmi wrote a book which was called Hisab al-Hind, the method of doing calculations as per the Indian techniques. So it is the methods of calculating as per the Indian techniques which became the source of the word algorithm. In fact, this algorithmic approach is something that is central not only to mathematics, It is something central to all Indian technical disciplines. Most technical discipline in India, most Shastras, they deal with various ways of doing things. The Shastras in India don't tell you various propositions. They don't tell you this is how the world is, or this is the origin of language, or this is the nature of life. They will tell you how to find out the occurrence of an eclipse, or how to do a calculation, or how to understand a certain imbalance in the body, or how to derive a word in a given language. So the rules given in the Shastras are generally called Vidhi, Prakriya, Karana. In fact, this board here, Lamba Jnanartham, Karana Sutram, Vrittartham. Lamba is the perpendicular. In order to understand the perpendicular, Karana Sutram, the rule which will tell you how to do this calculation, the next half verse is going to tell you. So the Shastras in India are not a collection of propositions, they are a collection of procedures. And over time, they try to change these procedures, improve upon them, make them more amenable. And the high point of our Shastras, one which everybody looks up to, the Shastra which really became the paradigm for all construction of other sciences, that is the Vyakarana of Maharshi Panini. That is called the Ashtadhyayi. That has a very high place in Indian tradition. And in fact, the common saying is, Kanadam Paniniyancha Sarva Shastropakaraka. In order to understand any discipline, you have to know the methodology of Panini, and you have to know the world view, the ontology of the Vaisheshika Shastra. Then you can go ahead and delve in any Shastra. And the approach of Panini is understood to be central to India, or all Indian disciplines, in the same way as the Western tradition acknowledges Euclid as the paradigm example of how a technical discipline is to be constructed. So here is an Indology scholar who is sort of saying, Euclid and Panini sort of hold the highest places in the respective traditions. Now what does Euclid do? Euclid tries to derive propositions from a given list of minimal set of propositions. And what does Panini do? He derives sentences from a given set of basic elements of language called Pratipadika, Pratyaya, and various other things. But the word derive is commonly used here, but the meaning is very different. In Euclid's derivation, he is deriving propositions logically from one truth to another truth. Panini is producing. The grammar of Panini is, as I said, not a set of statements about nouns always behave like this, verbs always do this. Panini is telling you, given the basic corpus of material of Sanskrit language, how to construct every valid word, every valid expression, every valid set of sentences corresponding to the meaning that you want to have. And that's what he achieves in terms of 4,000 to 5,000 sutras, along with a lexicon, what is called the Dhatu Patha, and along with a few other technical things that he needs. So the primary aim of the highest discipline in India, which is Panini's grammar, is very different from the primary aim of the highest discipline in the Greco-European civilization, which is to have a minimal set of truths about the world, and from them try to derive all possible, all known or knowable future truths about the world. Okay, now I will quickly now go through, because everybody who wants to know about Indian mathematics should at least know a dozen names, a dozen works which have played a very important role in the history of mathematics. So the Shulva Sutras are of very great antiquity. All scholars place them above or prior to 600 BC. We would like to place them somewhere around 2000 BC. Many Indologists will place them around 500, 600 BC. They are rules of constructing geometrical figures. Again, unlike Euclid's book, Shulva Sutras goes through a systematic set of procedures by which you can construct triangles, rectangles, squares, circles, and convert one figure into another, and construct more complex altars or yajna vedis which have complicated figures like the bird falcon figure, Shienachit, or all such figures. The other ancient period in India saw many texts from the astronomical Siddhantas. Unfortunately, we do not have any of those texts available with us today which can be dated exactly. As this is a book, we have an ancient Vasishtha Siddhanta, but we do not know when that Siddhanta was composed. Then when we come to the more classical period, the classical period for science is a very, very long one. In Greco-European tradition, the classical period runs from about 500 BC to about 400 AD, and it's over. And the high period of mathematics in this, at least as the way modern mathematicians would recognize, is only about 150 years from the time of Euclid, around 300 BC, to the time of Archimedes and Apollonius, about 100 BC. So most of mathematics that is regarded as high mathematics in Europe in ancient times was done in just this 150 years. Whereas we have had a very continuing tradition. Of course, Panini's Ashtadhyayi played a great role. The idea of zero itself is found in Panini. The idea of abstract formulae that we use in algebra goes back to Panini. The idea of a systematic set of rules and various conventions that we employ today, say in computer science, in terms of how one rule should block another rule, how one set of rules should have precedence over another rule, how to introduce one set of rules amidst another program. So all these things are found in Panini in very, very technical and nice manner. There is this science of prosody constructed by Acharya Pingala. This is the Chandas Shastra. The last section of this Chandas Shastra, the Chandas Shastra deals with Laghu and Guru, the short syllable and the long syllable. Then Pingala describes a very systematic way of how to write down all possible metrical forms or vrittas. Given n syllables, how many such vrittas are possible? Can I put them in an array? Can I put them in a sort of a matrix form? So all this involves what we today call as binary mathematics, many aspects of which, and combinatorics. Then we have many Jaina and Bauddha texts where many aspects of mathematics, especially different kinds of ideas of infinity, are discussed, ideas of logarithm, things like that. Of course, there is one great invention or discovery of Indians which cannot be dated. This is the place value system. I will say something about it later. The established place value form of doing arithmetic is finally found fully in Aryabhata's book, which is written in 499 CE. But Aryabhata's book, which has only about 108 verses, contains many, many, many more things. In about 30 verses, he covers most of the known mathematics. In about 20-30 verses, he covers the entire theory of measurement of time and keeping time and ages and eras. And another 30 verses, he does what is known as spherical astronomy, including methods of calculating eclipses and things like that. Aryabhata was followed by very important, of course, Varahamihira is a younger contemporary of Aryabhata. Then the Bhaskara that I mentioned to you, he is a very important mathematician. There is a very simple formula for the sine function which Bhaskara came up with. Sine function, as you know, is a fairly complex function which later Indians wrote as an infinite series. Bhaskara comes up with a simple polynomial expression, ratio of two polynomials for the sine function, which is used extensively in astronomy, which is accurate up to the level that astronomy demanded. All through the 0 to 90 degrees, the formula is very accurate. Brahmagupta is the father of algebra. In Brahmasputa Siddhanta, which was written in Bhinnamal in the Gujarat-Rajasthan border, he develops the mathematics of negative numbers. He develops how to do calculations with algebraic calculations with unknowns. He does lot of geometry, and he does some very interesting equations, couple of which I will tell you later. Then comes a period where these are the pioneers, Aryabhata, Brahmagupta. Their mathematics is carried on by a group of people which includes lots of names which I have mentioned there. And it ultimately culminates in Bhaskaracharya, who wrote the two famous books, Leelavati, Bija Ganita, and a book on astronomy called Siddhanta Shiromani. Bhaskaracharya lived in 1114 AD. He wrote his book when he was 36. He is supposed to have been born in a place called Vijayadavida, about the identification of which there are 2-3 opinions. It's Bijapur, or it could be other regions slightly northwards in southern Maharashtra on the Godavari bank. But in Patan, within 100 years of Bhaskaracharya's death, there is a temple where there is a huge grant given, mentioning the descendants of Bhaskaracharya and how his mathematics is taught there, and instituting a new grant for Changadeva, his great-grandson, how the activity of mathematics should be continued there. Bhaskara's books, more than anything else, they became textbooks. The book that he wrote on arithmetic and geometry called Leelavati got translated into Persian in Akbar's court by Abul Faizi. And the Bija Ganita, the algebra book that Bhaskara wrote, got translated during Jahangir's period by one Rushdie. Till the modern scholars, in the early part of 20th century, had started a campaign after the works of Bhaskara were found, that he is the last mathematician in India. So if you take up standard books on history of mathematics today, you will find the statement that mathematics in India ended with Bhaskaracharya too. It's only the work of last 50-60 years which has completely dispelled this kind of a canard, or whatever you may call them. Now there is a continuous tradition, as you can see. First, whole lot of books in regional languages started getting written. There is this Vyavahara Ganita in Kannada, there is Pavaluri Ganitam in Telugu. All these were written in 11th, 12th centuries. Then there are works in Prakrit. Then there come very important works like Narayana Pandita and the entire Kerala school, which I have summarized here. The Kerala school was started by a person called Madava. And we do not have any mathematical works of Madava, but we have two works of astronomy composed by Madava. Madava students and descendants, that's why it's called a school, because about 5 to 6 generations of scholars continued studying mathematics, continued studying astronomy, improving upon the methods enunciated by Madava. There were two crucial things that are important in this tradition. Madava himself wrote down very important results concerning infinite series. He wrote the infinite series for the ratio between the circumference and diameter of a circle, what is called the pi. And he not only wrote the series, he also told us how to do calculations with it so that we get good approximations. I will explain what this point means a little bit later. Similarly, he wrote down the infinite series for the sine function and the cosine function. Most of these series were later rediscovered about 200, 250, even 300 years later in Europe of 17th century. In the same way, Nilakantha Somayaji, who is the student of Madhava's student Parameshwara, this Parameshwara, who is in the bank of Neela in northern Kerala, he is well known for having observed the skies incessantly, carefully, for more than 50 years. And his student, Nilakantha Somayaji, comes up with a different planetary model. The main difference between the ancient planetary model and the planetary model of Nilakantha Somayaji was just this. In the ancient planetary model, the Earth was taken as the center of all planetary motion, and calculations were made that way. In Nilakantha's planetary model also, the calculations ultimately are made such that we are able to find out what is the position of a planet as seen from the Earth. But what are the actual orbits of these planets? And in that, Nilakantha, by comparing the motion in latitude and the motion in longitude, was able to come up with a formulation that the Mercury and Venus, which are the what are called the interior planets, their orbit is actually going around the sun only, and that their orbit does not enclose the Earth. Tair Brahmana Vrittena na bhuhu kabali kriyate. Tasmat bahireva sadha bhuhu. The earth is always outside the orbit of Mercury and Venus. This is the central feature of what we today understand as the sun-centered model of planetary motion. Now the Kerala school continued, in fact, in some manner till early 19th century, and then we had a great hiatus in Indian mathematics. There was really nothing much happening in 19th century. The old mathematical schools ceased to flourish and no new great mathematical school started. It was only in the 20th century when this nationalist spirit in India awoke again that we see flowering of mathematics, and it flowered in an extraordinary way in the work of Srinivas Ramanujan, and later on we will see many great scholars have followed this. Okay, this is a quick overview of the way mathematics developed in India. Now let us see some examples of the kind of mathematics that they did. So this is a sutra from Katyayana Shulva Sutra. It is explaining to you how to find out one square which is n times another square. So even in the ancient Shulva Sutra of 600 BC period, Indians are formulating a geometrical problem in algebraic terms. They are formulating a problem that given a square of side A, how to construct another side. The square of side A has area A squared. How do I construct a square which is of area NA squared? So for that a method is found which crucially depends upon the algebraic relation between n plus 1 into a whole squared and n minus 1 into a whole squared. This is done in 600 BC. Similarly, this decimal place value system. What is the central idea of the decimal place value system? It is representing numbers in an algebraic way. In fact, if I write the number 5205, it stands for 5 into 10 cubed plus 2 into 10 squared plus 0 into 10 plus 3. So it is something like the polynomial 5x squared, 5x cubed plus 2x squared plus 0 times x plus 3. So all our calculation that we do with numbers, division, multiplication, square roots, for which systematic methods were first provided by Indians, is based upon this understanding that numbers can be represented in an algebraic manner, and that is the place value system, and then you can manipulate with them. And in fact, in some later works, like this commentary of Ganesha Daivagya of 16th century on Lilavati that I told you, they are telling you even faster methods for doing calculations. Something like this vertically and crosswise method that many school children today know because of the great book of Bharati Krishna Tirtha Swamiji. Now, how did this place value system arise? The 10 as a basis was known in the Vedas. Numbers up to 10 to the power 12 and even larger are talked about in several verses of Yajurveda Samhita. The Upanishads have the idea of zero, have the idea of infinity. All of you know the words Purnamadaha Purnamidam, Purnat Purnamudachyate, that if you subtract an infinite quantity from another infinite quantity, an infinite quantity remains. The Bauddha and the Nayayika schools thought of Shunya and Abhava as philosophical categories. It is by this the idea of the number zero develops, apart from the idea of zero lopa in Panini's grammar. So zero develops this way, and already in Pingala's Chanda Sutra, written around 3rd century BC, you find zero being used as a marker in a sequence of calculations. And this idea of place value, that the number in the previous slide we saw, the number 5, since it has come in the 4th place from the left, it carries a place value of 1000. So this idea that the same number 5 in different places has different value, this became so commonplace that even texts in philosophy use this as analogy. I am quoting the Vyasa Bhashya of Yoga Sutra Patanjali. Tatha eka rekha shatasthane shatam dashasthane dasha eka cha ekasthane yata cha ekatvepi stri mata chochiyate duhita cha swasa cha iti. Meaning, When a woman in relation to others, at one place she is thought of as a mother, at another place as a daughter-in-law. In the same way, a number, when it is in different places, has to be thought of carrying a value of 1000, a value of 10. I mean, it became a common place in Indian thought that even later works of Shankaracharya has this analogy from place value that you will find. So ultimately, there is a well-known Buddhist work of 1st century of Vasubandhu, which also uses this analogy. So it became a common matter in philosophical circles. So ultimately, by the time of Aryabhata, we see that all calculations are made on the basis of place value, and in fact many more sophistications are brought into it. Inscriptions in India start showing numbers with place value system. Dated inscriptions that we have, the earliest is 1 near Gwalior, where this number 270 you are seeing. But there are inscriptions in Cambodia which are in Sanskrit of early 7th century, which give numbers with place value notation. That is, Indians had already exported this system to Southeast Asia by early 7th century. In fact, there is a Syrian bishop, Christian bishop around 660 AD, who is trying to put down the Greek thought to tell them that amongst the greatest achievements are actually done by Indians, and look at this wonderful place value system that they have come up with. This Ibn Sina, he is a very famous Islamic philosopher in 11th century. And he is saying that he went and learned the place value way of calculation from a vegetable vendor. So you should understand the nature of the methods that Indians developed. They developed powerful methods, not only which were powerful for the sake of being powerful, they were powerful methods that could be so spread in society that it could increase the mathematical culture of everybody. And this is no mean feat to say that an Indian vegetable vendor was a teacher of the greatest Islamic philosopher of the 11th century. A feat that modern India has hardly ever come to achieve. In fact, we are, if anything, till 20, 30 years ago, our vegetable vendors and our carpenters were very great in various ways of calculation. I think we are sort of trying to remove that capacity from our people rather than taking mathematics back to our society. This, of course, in Renaissance Europe, they recognized that the development of place value system was something as great, if not greater, than whatever the Greeks had achieved. Anyway, now coming to Aryabhata. So, by the time of 499 AD, as I saw, in 30 verses, Aryabhata is discussing whole of arithmetic, whole of geometry, lot of trigonometry, and quite a bit of algebra. And these are the kind of topics which he discusses. About 80 to 90% of these we teach in schools, meaning we in India had already developed and systematized the kind of mathematics that is currently taught in schools as canonical mathematics by the time of Aryabhata's work. But there are many, many things in Aryabhata's work, such as calculation of sine table, solution of linear indeterminate equation, what is called Kuttaka. We don't teach them in our schools, but they are extremely important, very nice mathematical methods. And if we were doing astronomy very seriously, as in ancient times, we would have been teaching all of that even in our schools or colleges systematically. Now I will quickly give you a bit of glimpse of the kind of mathematics that was followed from the time of Aryabhata till 17th century. Let us have some examples of highlights just to make these figures come alive to you. So here is Brahmagupta. He is coming up with this kind of a relation. There is a quadrilateral which is inscribed in a circle. It's called a cyclic quadrilateral. Brahmagupta was the first person to give these two relations for the two diagonals, the E and F in that figure, in terms of the four sides. So given the four sides of the cyclic quadrilateral, Brahmagupta gave the expression for the diagonals. If you multiply those two diagonals, you will get what is called the Ptolemy's theorem. EF is equal to AB plus CD. It is something like factoring the Ptolemy's theorem. This was, of course, rediscovered in 16th and 17th century Europe. The formula below is the formula for the area of a cyclic quadrilateral, which is due to Brahmagupta. This is just to tell you that very wonderful geometry was also done in India. It's not that Indians were only high in algebra or arithmetic, but were poor geometers. There is no such thing. In fact, even the circumradius of the cyclic quadrilateral could be calculated, various things. But all those results that the Indians gave were results like this. Given the sides of a triangle, how can you calculate various things? Given the sides of a quadrilateral, how can you calculate various... These are the kinds of results. Now I come to a very interesting algebraic problem done by Brahmagupta. This is a very famous equation, x squared minus dy squared is equal to k. In the bottom of this slide you can see the equation x squared minus dy squared is equal to 1. Here d is a given non-square number and you want to find out x and y in integers such that x squared minus dy squared is equal to 1. This equation nowadays is called the Pell's equation. Euler, the 18th century mathematician, gave this equation the name of Pell. Now what Brahmagupta did was, he took this equation, first proved a very general theorem. He said, you know how to solve this equation for some k1 and you know how to solve this equation for some k2, then you can find a solution for the product k1, k2. This is a very beautiful algebraic result, as you can see straight away. A result that was rediscovered by Euler in 1730, and Euler called it the theorem elegantissimum, the most elegant theorem in algebra. Now from this, Brahmagupta was able to immediately conclude that if you know one solution of x squared minus dy squared is equal to 1, you can find out infinite number of solutions. Now why is this equation important? Because if you want to find out a number like square root of 2, it is an irrational number, meaning you cannot write this as the ratio of two integers. But still you have to work with that number. This is what comes in all problems in architecture everywhere. So you have to approximate it. The Greeks went into a tizzy the moment they discovered the existence of irrational numbers. The whole world had collapsed. So that's why they were called irrational. But what the Shulva Sutras do is to give you approximations. So simplest approximation 3 by 2, 1.5. Next approximation 17 by 12. Next approximation 577 by 408. All these three approximations are solutions of this equation. If you put x squared minus 2y squared is equal to 1. X squared minus 2y squared is equal to 1. 3 squared 9 minus 2 into 2 squared 8 is 1. 17 squared 169 289 minus 2 into 12 squared 288 is 1. And the third level of this 577 squared minus 2 into 408 squared is 1 is what is given in Shulva Sutras as an approximation to square root of 2. So this is a very ancient problem. Now after Brahmagupta, a lot of things happened with this equation. Then a very beautiful systematic way of calculating it was developed, and it is presented in the Bija Ganita book of Bhaskaracharya. And Bhaskaracharya said, Chakravala midam jaguhu. People call this the Chakravala method. Later on people discovered that an earlier mathematician Jayadeva had already worked out this Chakravala method. This is the algorithm, I am not going to explain it. But I'll just give you one example. Following the way of Chakravala, you can solve this equation x squared minus 61y squared is equal to 1. Remember, you have to solve it for integers x and y, and not the trivial solution 1, 0. And the smallest solution for this runs to about 176 crores for x and about 22 crores for y. About 500 years after Bhaskara's book, in 1657, the French mathematician Fermat gave this as a problem, challenging other British and French mathematicians. You please solve for me this equation, and also you tell me a way of understanding that knowing one solution, how you can construct infinite number of solutions. As you can see, all this has already been done in the previous 500, 800 years in Indian mathematics. Indian mathematics, it's always said, is very application oriented. It's always used in astronomy. It is always used in architecture. But they did a lot of mathematics for fun also. So that's why I'm giving this beautiful work of Narayana Pandita. He wrote a wonderful book called Ganita Kaumudi in 1356. And he has given a very general way of constructing magic squares. And the method is very simple. You choose two arbitrary sequences as you want. 1, 2, 3, 4, 0, 1, 2, 3. If your problem is to make a square which adds up to 40, you do a small calculation to get another square, another sequence, 0, 5, 10, 15. Then put those sequences in those two nice manner. One set of sequence going up and down, another sequence going sideways. And then you do something called folding. Place one square over the other and add the numbers. And in the end, you will get a magic square. Now, this is not an ordinary magic square. This is something called a pan-diagonal magic square. A magic square is one where every row and every column adds up to the same number. Here it's all adding up to 40. Then the two diagonals should add up to 40. That is 17 plus 9 plus 3 plus 11 should be 40. 8 plus 16 plus 12 plus 4 should be 40. This is a normal magic square. A pan-diagonal magic square is one where even the broken diagonals add up to 40. That is, you start with 1, go up to 13, then come down to 19, and then go to 7. That also adds up to 40. Or you start with 18, go up to 9, then 2, then come down to 11. That's also 40. So you put it on what is called a donut or a torus or a vadai, and then go, you will get 40. This Varahamihira called it as Sarvato Bhadra. In fact, in Indian mathematics, magic square mathematics is called Bhadra Ganita, the mathematics of auspiciousness. It was not the mathematics of black magic that came in medieval Europe. Okay, finally about the Kerala mathematicians. So Madava wrote down this series for pi by 4. Paridhi is circumference, Vyasa is diameter. This series is nowadays called the Leibniz series. Leibniz rediscovered it in 1674. Madava is writing somewhere around 1400. Now, in this series, you all know pi's value 3.1415, etc. Even if you use 2000 terms in this series, you will get only 3.15. Though it's an exact result, it is a useless result for calculating. So, in the very verse where Madava is discussing this series, he is saying, Yat sankhya atra harane krite nivritta hritistu jyamitaya. When you go down in this series and start dividing by further and further odd numbers, you may get bored after 50th number or 100th number or 200th number. Then don't go doing this series. Do what I am going to tell you. Put a correction term in the end. So, the time when they were thinking of infinite series, at the same time they were thinking of correction terms that will give you a handle on how to calculate the sum of this series efficiently to the desired level of accuracy. So these are the two correction terms Madhava is giving. You go up to the number p in the series and then add that extra term. In fact, he has given a second correction term. So each of these correction terms are ratios of polynomials in P. And in fact, the second series of Madhava, with this correction term, you can use only 50 terms in that series and you will get the value of pi correct to 11 decimal places. Madhava, in fact, is well known to have calculated that verse of, this is a verse quoted in Nilakantha's Aryabhatiya Bhashya, Vibhuda Netra Gajahi Hutashana. This is all, the numbers are encoded in this in what is called the Bhuta Sankhya. Netra means 2, Gaja means Ashtadigaja 8, Ahi means Naga, Hutashana 3 fires. So like that the number is given, the number pi. It's a great, so Madhava is not only a discoverer of infinite series, he He is a discoverer of fast converging approximations. In fact, if you see the history of this calculation of pi, you will find a great development at the time of Aryabhatta, and the next great development comes at the time of Madava. And the most recent great development you find comes around 1910 in a result that Ramanujan published. He wrote down this result in 1910. He published it in 1914. In fact, using this in the 1980s, they were able to cross this what is called the billion number barrier in calculating pi. Of course, today pi is calculated, as I have told you, to 5 trillion places. Again, if you want to know the exact results for pi, pi is the ratio of the circumference and diameter. All the exact results that Madava has written down in 1375, you will see them repeated later under the name of Leibniz, Sharp, this Gregory, and various others 300 years later. Now, another major charge which has been placed against Indian mathematics is that they were like wizards. They wrote down results, but they did not tell us how they arrived at these results. Or, the other way of putting it was, in Indian mathematics, it's mixed up. This is what Al-Biruni wrote about Indian mathematics, that it is pearls and shells which are mixed up, that they have great results, but since they don't tell us how these results are proved, it is like mixing pearls with ordinary shells. Now, this is a major misreading of Indian mathematics. In fact, this is a problem that is common to the study of all Indian disciplines. We today print canonical texts of disciplines. Supposing we just had the Brahma Sutra and did not have the Bhashya of Shankaracharya or Ramanujacharya, we will understand nothing of the Brahma Sutras. But if that is all we had of Indian philosophy, so studying Indian mathematics merely by picking up a book of Aryabhatta or Mahavira or Brahmagupta, without going through what are called the traditional commentaries. Now, these traditional commentaries are of both types. In a functioning society, lot of this is preserved by way of teaching from the teacher to the student. And at some point, they are also put down in the form of textbooks and manuals and explanatory treatises. And it's true in modern science also, that you go to a great university to study, because from books alone, you will not get the heart of the subject. In order to understand the methodology of any subject, so many things are unsaid in books, they have to be studied. But there has been a discontinuity in the study of many of Indian traditional subjects. So at least we have to look at the way they were studied traditionally. We have to look at these commentaries systematically. Only then we will understand. And in fact, there are many, many such books which deal with the systematic exposition of mathematical results in India. There is a book called Ganita Yukti Bhasha, which is written in Malayalam. It was written in 1530. It reads like a modern textbook of calculus. It writes down every result of Madhava and explains how that is derived. The book does not have any diagrams, but they have beautiful way of explaining diagrams by word. He will say, draw a line from the northern corner to the southeastern corner, and from that point you draw a circle which goes to the west corner, etc., etc. So once you read it, you know the diagram. And then it will tell you the ratio of something to something is equal to something to something. And it's a book which has recently been published with translation and all that by Professor K.V. Sharma. It contains very detailed exposition of both the calculus that was developed by the Kerala mathematicians and also of the total subject of spherical astronomy and this Nilakantha's planetary model, etc. Now, coming to these proofs, these were called Upapattis in India. And this is a verse from Bhaskara's Siddhanta Shiromani. He is explaining what is the role of proof in mathematics. This is very important because this brings out the crucial difference with the way proof is understood in Indian tradition and the way proof is understood in the Greco-European tradition of mathematics. It's very crucial for understanding the foundations of mathematics in India. According to Bhaskara, what does the proof do? If one cannot demonstrate one's result, he says, one is that one is not clear of the result oneself. Nissamshayona swayam, one is not free of doubts. Second, Praudhim Praudha Sabhasu Neti Ganaku, that a mathematician will not be accepted as a serious mathematician in a community of mathematicians unless he can show how his results are demonstrated. The same thing, a student of Bhaskara, that is Ganesha Daivagnya, much later, he is saying the same thing. What is a proof supposed to do? If you find a result, it should be publishable in a journal. What is publishable in a journal? It is sent to 100 referees or 20 referees or 5 referees. They go through. So the peer group says, here is a result, here is a proof. And second, the author himself has to be clear, so he has to put it down on paper. But mathematics is supposed to be much more than this. The way Greeks explained mathematics was, it's almost like reaching the God. Mathematical truths were to have been demonstrated once and for all, irrefutably, eternally, absolutely, whatever be the words. If you read the Greek literature of Plato or Aristotle or the commentaries of Proclus on Euclid, these are the words you will see. That mathematical truths are truths made in heaven. But for Indians, mathematics was one more earthly science like all other sciences. Its methods of proof, its methods of justification were the 4 or 3 pramanas, whatever we accepted, and Anumana was only one of them. Pratyaksha was as good. To show the Pythagoras theorem, Yukti Bhasha says, cut this right angle triangle in this way, turn it around, put it somewhere else, cut something else, and then finally say, see, this square on the hypotenuse is equal to the square of the 2 sides. Such proofs Euclid will not accept, because these are dependent on Pratyaksha. Of course, this is dependent on other geometrical arguments also. So what I am trying to tell you is, Indians did not equate mathematics with proof. Mathematics, like science, was as much, laws of mathematics were as much a matter of discovery as of proof. The excessive emphasis on proof, in fact, has destroyed a lot of contemporary mathematics, and in one crucial case where it did destroy is the case of Ramanujan. Ramanujan wrote, before going to Hardy, he wrote down all his results in 2 notebooks. And once he went to England in 1914, he got busy with some other mathematical work with Hardy. And then when he came back, he got busy with some other subject called Mach theta functions. So all these 2 notebooks were not published. The results in them were not published. It's only in the last 25 years that the 2 notebooks of Ramanujan have been fully analyzed. And then the work that he did on his deathbed in the last 1 year has also been analyzed. So these notebooks that he took before he went to England, this is the kind of thing that scholars are finding today. It contains about 3,000 claims. And Hardy at that time thought over 2/3 of them were old. What did it mean? Hardy did not think that they were not correct. He thought that Ramanujan was writing this result about continued fraction, this result about elliptic functions. So he thought that they were all ones which had been discovered in 19th century Europe. But now the scholars say more than 2/3 of Ramanujan's work in his notebooks were new at the time he wrote them. And this author, who has written 5 volumes on the notebooks of Ramanujan, he says hardly 4 to 5 results are wrong. So here is a man who in the age group, I think he is 27 when he leaves for England. In between his 20th and 25th year, he has written down these 3,000 results. And later on his deathbed, he is writing about 600 results. And in fact, there is a story that Littlewood tried to go and teach Ramanujan some modern mathematics, etc. The moment he would start saying something, Ramanujan would start writing down some results. So he would hardly listen to an exposition of new branch of mathematics without discovering to first make sure that these results are correct by your methods. My methods, I will communicate to you because I cannot write them down in a letter or a brief piece of paper like this. They are indeed based upon systematic work, and we will discuss that, and I am for publishing all the work of mine systematically. So this became an issue all through Ramanujan's life. Not only all through Ramanujan's life, in fact, in the next 100 years, we have not understood Ramanujan because we have been viewing him from a framework of mathematics where mathematics meant proof. So in terms of proofs, Ramanujan proved nothing. But in terms of results, he gave 4,000 results, which kept the mathematicians of the world busy the next 100 years to keep proving them. And if the proof was, if the idea of the proof is in the pudding, there was hardly a result that was wrong. And here is a man who says, I have a method. Now, what is the message of all this? I think if we have to really understand Ramanujan at some level, we should look at him from a different tradition, that proofs are important in mathematics, but they are not the be-all and end-all of mathematics. Mathematics neither begins with proofs nor ends with proofs. They are a way of functioning of the mathematical community, going from known knowledge to further knowledge. There are, of course, several other technical features of proof in Indian mathematics, which I will just briefly put here. That Indian mathematicians do recognize results in mathematics should be proved. They don't believe that even giving 20 or 100 or even a million examples or even infinite number of examples to justify a result is a proof of a result in mathematics. So you need to have logical arguments, etc. And all these commentaries do give proofs. Some of them are published. Hundreds of them are lying in mathematics, in manuscripts, and maybe millions of them have been lost in history. The proofs are presented in a systematic manner. They go from known to unknown. And many other kinds of physical arguments, that is arguments based upon the nature of mathematical objects, do play an important role in mathematical proofs. And the main purpose of proof was to enhance the knowledge of the community. And the method of proof called proof by contradiction, what is called tarka in Indian mathematics, that is given a somewhat of a lesser role. If any of you have tried to read the elements of Euclid, you will find that about 80% of the proofs are based upon what is called reductio ad absurdum. That you assume the contrary of what you want to prove and show that you come with a contradiction. Indians very rarely use this. And they don't use it to show the existence of something whose existence cannot otherwise be proved by direct methods. So in this is something called the constructivist philosophy of mathematics of today. So if you want to find out the way Indian mathematics differs from either the mathematics that the Greeks did between Euclid to Apollonius, or the mathematics that has been going on in the last 150 years, say from the time of Dedekind and Weierstrass through the Bourbakis to the modern time. The main difference is this, that the Indians don't use the reductio ad absurdum technique. They don't believe that proof is all in all. And they did not set up an axiomatic system. Though they went from known results to unknown results, they did not set up an axiomatic system. And this is a technical point which is related to reductio ad absurdum. Because if you have an axiomatic system, then you take any other result and show that it contradicts this. Then that will be a proof of that result. But in a mathematical tradition where results are proved constructively, you don't need to specify all axioms once and for all. And in fact, Indians never believe that all assumptions can be once and for all stated for the future generations. You have to, whenever certain question arises, you will have to refine your proof. In fact, what the history of mathematics shows is the kind of picture that the Indians had of mathematics. From the Greek or the modern canons of mathematics, Greco-European tradition was barren, as I said, except for 200 years then and for 150 years. And the greatest discoveries that Europe did of mathematics during the Renaissance were all done upon methods based upon what is called imperfect intuition or imperfect induction or arguments, approximate arguments. Every result of Newton is proved that way. Every result of Fermat or Descartes is proved that way. And one historian has written, if the Renaissance Europeans had taken the Greek word seriously, mathematics in Europe would have been a dead subject. But in India it was never a dead subject. It was continuously alive. It had a very rigorous philosophy of its own. But it did not think the ideals of the Greek mathematics, which are in fact abstract ideals, which are not relevant for science, or which are perhaps not even relevant for mathematics, as attainable or even desirable ideals. It had its own notion of rigor, and that did bring a continuous tradition which is perhaps reflected even in the work of Ramanujan. In fact, if we want to understand Ramanujan, we should perhaps see that he is somebody in continuation with the Kerala school, someone like Madava. Recently I have given this quote, which in a paper that I circulated, mainly because Professor Mumford, one of the current leading practicing mathematicians in the world of modern mathematics, has tried to understand that the Indian tradition is indeed constitutes a different way of doing mathematics, at least the way, a valid way that has evolved in history. Mumford may not think that it's too relevant for today, but his understanding of history is that this does represent a legitimate way of doing mathematics and arriving at important and beautiful mathematical results without going through the Greek canon. In fact, understanding Indian mathematics has, the greatest hurdle has been our sort of ignorance of what this Greek canon of mathematics is all about. So to summarize, before that, just one point, that I told you that the two great Renaissance discoveries, differential calculus, integral calculus, and also the altered planetary model of the universe, a different model of the planetary system. All these were given by Kerala mathematicians between 1400 and 1500, and they are claimed as the hallmarks of the ushering in of modern science in Europe. About 200 years later, the philosophers of science and historians of science who studied Chinese science, they also discovered wonderful things. They found that the science and technology as practiced in China in 1600 was superior to whatever the Europe knew at that time. But Needham from there went on to the question, it was true that China was superior in science in 1600, but the scientific revolution happened only in Europe. And then the rest of all his historical research and the historical research that followed Needham went into this stupid blind alley. Why did the scientific revolution, why did it not take place in China? Or recently I attended some conference in mathematics where I presented something like similar history. So somebody got up and asked, why didn't Indians know about Euclid? So I asked him, why didn't the Greeks know about Panini? If the Greeks were so well, if the Indians were so well conversant with the Greeks by the soldiers or philosophers who came along with them, the Greeks would have been as much conversant about India. Why didn't the beautiful Indian science of prosody never went to Greece? Why didn't they understand Panini? And they were doing what was called this rhetorical grammar for the next 1500 years. So civilizations don't function that way. They borrow, they take, but they move on their own inspiration. They move on their own they move on their own genius. So unless we understand this, we will be caught with this Needham kind of question. Why didn't we do this? Why didn't we do that? Instead, we should be asking the question, what would we have done if this Kerala school had continued, if the Dutch and the Portuguese did not ransack Kerala in 16th and 17th century, what would have happened to mathematics in Kerala or mathematics in India? So these are the kind of issues. And unless we understand the roots of our own creativity, we will not be even able to appreciate the great geniuses that India has produced in 20th century, someone like Jagdish Chandra Bose or Prafulla Rai or C.V. Raman, needless to say, Srinivas Ramanujan. So this methodology that Indians presented in mathematics is something very crucial. It's crucial for the philosophy of science, history of science, but more than anything else, I feel it's very crucial for mathematics education. We have converted mathematics education into a matter of learning proofs by rote. Learning by rote of proofs, which don't make sense to all the students. Proofs should be there, they need a place, but much more should be known. We are teaching number system to our students saying, numbers satisfy associative law, commutative law, some other law. They don't know how to add half plus 1/3. This is no mathematics. The Greeks separated their philosophers from their ordinary men. And Plato thought that the philosophers only need to know theory of numbers. They don't need to calculate anything. Euclid is supposed to have thrown a coin at somebody. Someone asked him, how do you calculate this? He said, give it to a slave. He will calculate it for you. Or today they might have said, write a computer program for it or whatever. But I think a wide mathematical culture where the vegetable vendor could teach the greatest Islamic philosopher would be lost unless we take it upon ourselves to teach the central features of our mathematical tradition. There are extremely beautiful set of problems in each of our books which make sense to our students. There are extremely nice calculational techniques which are scattered all around our ancient mathematical texts. We have to make them a part of our current mathematical education. By that, we may hope to make it a continuing part of our future mathematical heritage. Thank you.